All right, we're trying to find the length of the shortest path from S to T. And what we're going to do is for each node, we're going to find the length of the shortest path from S to that node. And to keep, just because it takes up so much space, we're not going to store the path itself. We're just going to store the cost of the optimal path and which edge was the last. So here, for example, if you want the shortest path from S to this V7, the length of the shortest path will be 9, and the last edge in the path will be this one. And if you remember when we were doing depth for search and stuff, that's enough to follow the path back, right? So if you want the shortest path from S to V7, you follow this edge, and then you follow this edge, right? Everybody remember that? So suppose in a loop invariant sort of way, we've filled up the answers up to here, right? We've found the answer for each of these nodes. And now our job is to find the answer for this node, right? So we want 7, I guess, will be the cost of the minimal path. And the last edge will be this, where did the last, there it goes. That would be the last, that's the answer we're looking for, right? And why is it 7? Well, it's the length of the shortest path from S to V8. That, well, let's see if we can compute it. I could have it wrong, but we can ask the bird which edge do we take last, and there are 2 possible edges, right? So since we don't have a bird, we have to try them all, right? So if she says take this edge last, then we can back step along that, and then what we need is the best path from S to this guy, which our friend tells us is 6, and then right, then we combine those to get our 7, right? And then if our friend says this edge, then we follow backwards and we combine the cost that the friend says to get here plus the 7 to give us a 9. And then we've done both of them. So we take the best of the best and we get our 7, right? Everybody kind of follow that? And then we go down and do it again, right? Our goal is to find the shortest path and the edge. And how do we do it? If the bird says this, then we combine and get 13. If she says this, we combine and get 17 and so forth. Right, everybody following that? Any questions about this algorithm? Yeah, so if we were doing recursion, then this is a smaller subinstance that we could ask a recursion friend. But in fact, we won't be doing recursion, we'll be doing table lookup. So each subinstance will be stored in a table, right? Does that make sense? In the node. Yeah, that's kind of what I'm doing here. Exactly. Any other questions about this algorithm? All right, so then you find the best of the best. And then how do you, once you fill out this table, how do you find the optimal solution? Well, you just, as I said, you follow the pointers backwards, right? You have the friend's advice, the bird's advice, which you follow backwards, right? Everybody got that? I must admit, so far, this seems to be going better. Usually I'm trying to explain, the whole nuance of dynamic programming. And now I'm focused on just this one dynamic programming algorithm, and it makes it easier. All right, so then we're going to have, you need some sort of data structure. I was storing them in the nodes, but usually we put them in a table. So for each sub-instance that we have to solve, we have an entry in the table. So in this one, I've labeled V3 because it's trying to find the shortest path from S to V3, right? So you need to know what the set of sub-instances that you need to solve, and what do you store in there? You store the cost and the bird's advice, which was the last edge, right? Everybody following that? And that's the base case. So you do that first, and that's the entire problem. So you do it last, right? Yeah. Yeah. So in dynamic programming, I mean, here we can think we're following the edges of the graph. Often we're doing it in a table. So you just go through the table. All right. So